You have a bottle of this at home. It's aspirin. And by fun, I mean, haven't you ever thought of throwing it in a round bottom flask, dissolving it in some chemicals and blowtorching it? No? Just kidding, that won't do anything. Jokes aside, for the past 30 days, I played around with this secretly fun chemical known as acetylsalicylic acid by extracting it, purifying it, and transforming it. And despite it taking so much work, it genuinely surprised me how much chemistry these pills can do. Little did I know, this would be the most intense and mentally draining video I've made on this channel yet. So without further ado, Step 1. Pulverizing. All great chem experiments start with the most boring, tedious, repetitive work, and that's exactly what I do here, hammering and crushing the pills. I had to dump them out on some paper and gently crush them into rough pieces. I mean, it may be tempting to absolutely obliterate them, but then they'll fly everywhere and I actually care about my yield here, guys. By the way, I got some white pills instead of blue ones, as the dyes would be a pain to remove. I didn't directly choose a mortar and pestle as it often doesn't work great for crushing large objects like these. After a couple of minutes of hammering them into rough crumbs, I felt it was good enough, and then I transferred everything into a mortar. Now I can pulverize it further using a mortar and pestle, and with ease, the pieces are grinded into a fine powder. Finally, I can transfer it into a beaker and move on to the next step. Step 2. Dissolving. Anyone who has seen my post would know that I recently acquired like a 20-liter drum of pure acetone, and although it is a massive fire hazard, wait, you know what else is massive? The fact that it is also probably the greatest purchase I have made in my entire life, costing only $120. In all fairness, it's a really useful chemical and today I'm going to use it as my solvent. Now you might be thinking, how is carbon ever going to pour it out? Now I could have just tilted the entire drum of acetone, but that would be what we call in chemistry a career-ending move. I do have a good idea though, and that is to simply use a siphon. I just need to connect a tube to the upper opening and suck a little out using a handheld pump, guys, not your mouth please, because accidents happen. Seriously, don't try to drink this one unless you're aiming for the fastest hospital speed run ever. Then, reversing the tube, as long as the other end is lower than the liquid's level in the jug, it will continue to pour out until it reaches equilibrium. This is really cool, almost kind of magical, and it's also how toilets can flush without using electricity. When I finally dispense enough liquid from my acetone station, I can stop the flow and bring the undissolved acetone and aspirin over to my fume hood and place it on a hot plate. Now just like when making your favorite hot chocolate, I also need to make it hot and mix it around, but without the chocolate part. Instead, only the aspirin of the aspirin pills is dissolving in the solvent, and all the white stuff floating around in a suspension is a filler. This could be like inorganic salts, cellulose, starch, and talc? Which is apparently baby powder? Anyways, let's not ask too many questions, but I do have to say this thing does look like milk. After heating and stirring for a couple of minutes, we can then take it off the heat and pour it through a gravity filtration using a fritted funnel. Now yes, I learned my lesson. Usually we want to use gravity filtration when we collect the liquid and vacuum filtration when we want to collect the solid. Here we don't want the solid filler, only the acetone solvent that contains the aspirin, so we patiently wait for it to all drip over. This did take a while, but in the end we can see the separated baby powder on top. Step 3. Undissolving. Now that we have dissolved all the aspirin into the acetone, we need to remove the solvent now to recover our aspirin, technically undissolving it in many ways. This can be done simply by evaporating off the solvent in a well-ventilated place, but I also like to finish my experiments before I retire. I really treasure my acetone too, and I don't want to lose half a liter, although it's like only 2% of my entire stock. So we do evaporation with a twist, turning it into a distillation. Now I was lazy and I didn't really want to make an entire distillation setup, but in all fairness, I actually did it just because I wanted to test out this really cool new piece of glassware I got called a short path condenser. I do want to point out that short path distillation is generally not recommended for volatile solvents like acetone, and we usually use it under vacuum. So it's definitely not recommended, but I wanted to flex my new glassware. Yo, sometimes the drip matters more than the method, you know? That's probably the worst possible thing for a scientist to say. Anyways, I decided to go with it, and as it got boiling, it was a bubbly one. Volatile solvents like this also distill very quickly, and the temperature on the thermometer only hits around 56°C, which is exactly the boiling point of our acetone. It was dripping very quickly indeed. distillation neared completion, the aspirin all crashed out of solution and I was left on the other side with half a liter of pure recovered acetone. Now I just need to dig out all of my aspirin from this Erlenmeyer flask, which was annoyingly difficult. I mean, can you imagine if all of our dishes were shaped like this? Finally, I rinsed the inside with some more acetone just to make sure I collected everything, and left the wet powder to dry in a well-ventilated area over a couple of hours. Step 4. Crystal growing. When I came back, it was drier than the Sahara Desert and it was surprisingly difficult to crush. It all formed one big chunk, and so I had to use a good amount of force to really break it apart. After struggling with it for a few minutes, I felt it was good enough and put it aside. Now I just need to make some hot water. No, not for my tea or anything, but for a recrystallization. I just need to make sure to crank up the heat and cap the flask. No, I'm just kidding. Never do that. Things can explode, alright? Anyways, the water took a surprisingly long time to heat up. When it was like 80 C and above, I felt it was good enough, but also because I was bored of waiting. Finally, I grabbed a beaker and poured some water in. To my surprise, it rapidly started to flash boil, and so I added more water in to calm it down a bit. Now in this hot water that was nearing 100 C, I quickly transferred in all of our impure acetylsalicylic acid and tried to make it dissolve. Now I think it got pretty transparent, but the bubbles from the boiling may have obstructed this fact. I felt it was clear enough, and so I took it off the hot plate to let it cool down slowly. Now what we're doing here is a lab technique known as a recrystallization, which is used for purifying solids. Although our extracted aspirin may have seemed pretty pure, there is actually still a good amount of other salts or impurities that have incorporated itself into the crystals in the powder, which is kind of a problem. To get rid of these, we have to dissolve our solid in a liquid such that at a high temperature it's extremely soluble, but at a low temperature it's very insoluble. Conveniently, a great solvent that matches these criteria for aspirin would be water. This way, we dissolve the crystals like we just did in boiling hot water, but as we cool them down, we reform them, and they form in a much purer fashion, with the impurities staying in the solution. This is because it is thermodynamically favorable, and by kicking out these impurities, the resulting system possesses lower free energy, as there's more entropy. Think about it, the yellow particles used to be locked in the lattice, but now they can flow around randomly and freely. Anyways, back to the beaker of crystals. It looks pretty beautiful as aspirin forms these nice thin needle-like crystals. To really push out an extra gram or two of aspirin though, I also prepared an ice bath to put the beaker in after it lowered to room temperature. By bringing the temperature even lower, the solubility decreases more as well. When as much aspirin that could come out recrystallized out, I figured it was time for the next part. Step 5. Separation. Now after crushing up the crystallized aspirin in the beaker, we can then pour it through a filtration, but this time, we can use a vacuum as we are collecting the solid here. After pouring it onto the fitted funnel, I pull the vacuum and water is instantly sucked away. I also made sure to wash the aspirin with a bit more water to really flush away any remaining impurities, and I also rinsed the beaker to maximize our yield. Even as it seemed that all the water had left, I continued to keep the vacuum on and pulled it harder to really drive off as much moisture as possible. I only have a handheld pump, so I continued to pump it until my hands started cramping. Although tiring, it is an effective way to dry stuff, but when I do have the chance, I'll make sure to get a real vacuum pump. Step 6. Drying. To fully dry it though, I finally transferred all of our aspirin powder into a metal tray and put it into the oven on low heat to let it slowly desiccate over the span of a couple of hours. However, do be careful though, pure aspirin surprisingly decomposes at a very low temperature. And I mean like crazy low, like 140 C. I used the lowest heat setting possible on this and it's somehow still as hot as the surface of the sun, so it decomposed a bit, forming salicylic acid and vinegar. In hindsight, it might have been a good idea to use a hot water bath, or if you have access to one, just simply use a lab oven that has controlled temperature. Anyway, stuff happens, but on the bright side, this wasn't horrible as I was planning to transform the acetylsalicylic acid into salicylic acid anyways. On this topic, I stated earlier that acetylsalicylic acid is a really fun chemical because it is not only a good medication, but can be used in a variety of home synthesis as well. For example, this is due to its structure. If we take a look at a 3D model of it, and if you know your functional groups, you can spot an acetyl group, a methyl ester, a benzene ring, a carboxylic acid, and a phenol if we remove the acetyl group, which is in the case of salicylic acid. This abundance of functional groups allows us to do a lot of transformations, and the possibilities are really endless. For instance, our starting acetylsalicylic acid can be hydrolyzed, either using acid or base, to form salicylic acid, which is often used in skincare. Salicylic acid can then be decarboxylated, removing the carboxyl group and forming phenol, a useful industrial chemical that is also formed in the cumene process. This can then be reacted with acetone to form bisphenol A, or BPA, the plastic, or it can be nitrated, reduced, and then acetylated to form Tylenol, a series that Now Red did back then. Salicylic acid can also be esterified to form methyl salicylate, also known as wintergreen, or it can be oxidized to form quinones. Lastly, condensing phenol with formaldehyde gives us Bakelite, one of the first plastics ever made. These are but a few of the possibilities that the world of chemistry allows, and it always seems so strange to me how matter is so interconnected, how changing some atoms from medication can lead to plastics and fragrances. You remove one group, and suddenly you've gone from medicine to skincare to plastics. Geez, this molecule's got more career chances than me. In this video, I'll cover up until its hydrolysis to salicylic acid, and I'll save some other reactions for the future. Salicylic acid is made when our acetylsalicylic acid is heated up, which is what happened by accident earlier, but it can also be done through a more controlled hydrolysis process, either using acid or base. Hydrolysis is when water is used to break apart a molecule, and in this case, it's the reverse of a methyl esterification. In Fischer esterifications, a carboxylic acid reacts with an alcohol to form an ester and water, and in hydrolysis, an ester and water react to form a carboxylic acid and an alcohol. By reacting our acetylsalicylic acid with hydrochloric acid, the acid I'll be using here, the byproduct carboxylic acid is ethanoic. There is one big issue with this reaction though. Its equilibrium position is relatively unfavorable, and the reaction does not go to completion in normal stoichiometric amounts and conditions. This is why we want to use a huge excess of water to push the reaction to the right. Again, we are leveraging Le Chatelier's principle here. We also want the reaction to be hot at boiling temperatures so that it can react at a faster rate. So here you can see me scooping out the acetylsalicylic acid that I tried to dry, with some of it turned into salicylic acid. I'm weighing it just to get a rough idea of the amount of reagent I have here, even though I know that it's not exactly pure. After getting it all in the beaker, it came out to around 38 grams, and I crushed it down further as some of the pure aspirin was still in chunks. When this was finished, I finally grabbed my 1 liter round bottom flask and placed it on top of a retort stand. Above that was a powder funnel so I can transfer in the reagent without spilling. And I mean, you guys definitely noticed this upgrade. In the past, I've always used plastic funnels, and now that I have one, it feels like such a luxury. Anyways, all of the nearly pure aspirin was transferred in, and after that, I poured in about 600 ml of water, which is a large excess but also such that the recrystallization solution in the next step is nicely saturated. Lastly, as seen in the reaction equation and also the name, acid catalyzed hydrolysis, we're going to need a strong acid, and I chose to use hydrochloric. So around 10 ml of 37% HCl was poured in. Then, the powder funnel was removed, and I moved the round bottom flask onto a hot plate. Following this, I just had to put the last part, a long reflux condenser, on top of the flask. Now, we can finally start our reflux by turning up the stirring and the heat. Now at first, it looked like nothing much was happening, but this was probably because it didn't get hot enough yet. Much of the acetylsalicylic acid still remained undissolved even after 15 minutes, and I started to worry. Maybe all of this effort went to waste. Maybe this wasn't acetylsalicylic acid, but salicylic acid. Maybe my chemistry skills were non-existent. Maybe I accidentally got ibuprofen pills. Wait, nope, never mind, it started dissolving. After that existential crisis of staring into that flask for like half an hour, I realized that it's not heating up enough because it isn't insulated well, so I decided to just add some aluminum foil. This can trap some of our heat. After another solid 5 minutes, you can see that all of the powder basically disappeared, and the solution finally cleared up. Now I was pretty excited to start the reflux, but one thing kept bugging me. I'm not sure if you could see it here, but there were some dirty things inside the round bottom flask, like some brownish particles that wouldn't dissolve. And I'm pretty sure it came from the time when the aspirin burnt a bit. I also think the solution was quite cloudy, and although I couldn't be sure whether it was due to the temperature not being high enough, or just truly some impurities that got through, I decided to go for it and get rid of it through probably the most risky thing I've ever done so far, which is a boiling hot filtration. These are generally really risky because, so many things could go wrong, right? If it cools down just enough, all the aspirin would crash out, clogging my filter, and I wouldn't be able to get the rest through it. Pulling too hard on the vacuum could also cause too much water to boil and let all the solid come out as well. So I spent a solid 10 minutes getting my extremely sophisticated setup ready, which was 1. A vacuum filter, 2. An Erlenmeyer flask underneath, 3. My 1 liter round bottom flask on top of the hot plate, 4. A retort stand on the right, 5. A heat gun to keep the setup hot, 6. Some heat resistant gloves, and lastly, my handheld vacuum pump. With all of these materials ready, I was confident yet still afraid my entire month's work would go to waste, so I just held my breath and went for it. Simultaneously, I had to dump in the solution on top of the vacuum filter, pull the vacuum moderately, not too hard or too weak, have my right hand keeping the 1 liter round bottom flask on the hot plate so the solid wouldn't crash out, and wield a heat gun with my left hand so that the solution wouldn't cool too much. This was definitely the most intense multitask I'd done on this channel yet, and I really wish I had a third arm for this. I kept on pulling the vacuum until my arms got tired. I had to keep it up for a solid 5 minutes in order for all of it to pass through, and when it finally did, I was pretty relieved. As you could see on the bottom of the Erlenmeyer flask, it turned pretty cloudy, and this was because I wasn't keeping it hot. Finally, placing this back on the hot plate, I can put back on the condenser and get to the reflux. As soon as the solution cleared up and started boiling, the reflux can be started and run for around 20 to 30 minutes to ensure that the reaction reaches equilibrium and forms the most product possible. Now what's happening during this reaction was, as I stated, an acid-catalyzed hydrolysis. But what's really happening? I mean, there's more to chemistry than just the equation. This is where we get into the mechanism of how it works, and it is wildly fascinating. So first we have our reagents, our acetylsalicylic acid and our acid catalyst in water forming hydronium. What's first going to happen is that one of the electron pairs on our carbonyl oxygen is going to get protonated, stealing a proton and turning the hydronium into water. However, this positively charged oxygen is unstable, so the water is going to come back and attack the electrophilic carbon, pushing an electron pair and attaching itself on, forming an oxonium ion. Next, another water molecule from the solvent will come in and protonate itself by removing one of the hydrogen atoms, forming hydronium again. Now it may seem like everything is looking pretty stable, but the ether oxygen isn't happy, and so it's going to get protonated again, forming a good leaving group. Now the entire group can simply pop off with an electron pair donation by one of the alcohols, and the entire thing falls off. You can now notice that this is in fact ethanoic acid but with a protonated carbonyl. And since it doesn't like that extra hydrogen, it'll just donate it to the water. Now you can see all of our products formed, just like in the equation. Our salicylic acid, our acetic acid, and our acid catalyst. Isn't it just amazing? It's like in math when all the terms cancel out. Do keep in mind though that any of these steps can happen in reverse, depending on whether the conditions are favorable or not, and thus this reaction is in whole an equilibrium reaction. Now back to the lab, the reflux was going pretty well and 30 minutes had about passed. I mean, refluxing kind of makes me feel like I'm cooking something, but my dinner doesn't usually come with an SDS sheet. After all, chemistry is cooking, right? Anyways, I turned off the heat and slowly let it cool. Step 8. Recrystallization. Now it's our second recrystallization of the video, and that is the recrystallization of our salicylic acid. Now what's interesting is usually in videos of other chemists, you can see that the crystals form nicely in long, sharp needle forms, from bottom to top. But mine kind of just turned from clear to cloudy, like, where are the crystals, bro? Or microcrystals forming in suspension? I'm not sure if it's because my solution was too super saturated, or if it was because of the lack of a nucleation site. Although I think I spoke too early, as after waiting an entire night for it to cool down, you can see some more defined crystals, which is really fascinating, especially their shape. Like the aspirin crystals, they form long, thin, clear needles, and it's a pretty unique property of these organic compounds. Anyways, I waited patiently for it to cool down to room temperature and then moved it into an ice bath to squeeze out an extra gram, as I'm actually aiming for a decent yield, unlike previously. Now when it reaches 0°C, it's time for the last step of this entire month-long process. Step 9. Separation. Now as I stated, the final step of this process is to bring out the salicylic acid and separate them, then dry them. This can be done by first pouring out our solution along with some crystals, and to my surprise it formed a pretty cool glitter snow globe-like effect. After digging some more and washing the Erlenmeyer flask, I was able to get all of it out. Our salicylic acid was then washed with some more water and mixed around to really make sure all of the side products are removed, namely the acetic acid that also formed. Finally, I then pulled a strong vacuum on it for a couple of more minutes, although I also really wished I had a vacuum pump as my arms were really getting tired. Also, for anyone asking, yes, contrary to popular belief, I have a handheld pump not because I'm broke, but because it's a good forearm workout, Any time's a time for gains, right? When it was dry enough, I then had to scoop it all out and put it on a plate. This time, I learned from my mistakes and made sure to not use any heat, as I don't want to risk it decomposing into toxic phenol. Step 10. Analyze. Now after drying, this is my final salicylic acid product, and it's this snow white powder. It looks really beautiful and it's the fruits of my month-long synthesis, and I'm glad that it all worked out pretty well. I can also finally weigh it on a scale, and my final yield totals up to being around 54%. I'm not sure if this is actually a good yield. I mean, it's kind of low compared to my other experiments, but by the way, this is actually a pretty good yield, considering that this is a linear synthesis instead of a convergent one, where the reactions are done consecutively on each previous product. This means the yields in my step of extracting my acetylsalicylic acid and the hydrolysis step to salicylic acid must be multiplied together in order to obtain the final yield. What's also really cool is that there's also a phenol test I can do with salicylic acid. Since I don't have an NMR, a decent way to verify if I have actually formed salicylic acid is to use iron 3 chloride, which when reacted with phenols will form a purple complex. As you can see through the structure, salicylic acid has a phenol group, but acetylsalicylic acid does not. As expected, when I dissolve some salicylic acid in ethanol and then put some dilute drops of the iron 3 chloride, we see a nice purple color forming. Along with this, I sincerely want to thank you for following me along this journey and making it here in the video. Step 11. Subscribe to Carbon. Step 12. Support Carbon 12. Isn't it cool how Carbon 12's video has exactly 12 steps in it? Pretty cool coincidence. Anyways, I really want to thank you dedicated viewer, but also my patrons, whether on YouTube or Patreon, for making these projects affordable, and I'll provide behind the scenes, early access, shoutouts, and more. If you would like to support a high school student like me, just a couple of dollars would go a long way in helping this channel to continue providing quality and educational chemistry content. Anyways, thank you so much for watching till the end, and please consider clicking the subscribe button below.